Early Earth had no oxygen. So why do we have it now? How does photosynthesis evolve? To solve this mystery, let's take a look at Earth's timeline. Scientists have theorized Earth to be more than 4 billion years old. In fact, the first part of Earth's history is known as the Precambrian period. The Precambrian period ranges from the beginning of Earth up until the appearance of multicellular organisms. Within, it consists of three eras: the Hadean era, the Archean era, and the Proterozoic era. As the story goes, 4.6 billion years ago, in a period of the Hadean era, Earth was a giant molten rock filled with helium and hydrogen. Since there was no oxygen at this time, Earth did not have an ozone layer, which prevented the protection from harsh UV rays. Not only was Earth highly radiated, it was completely inhabitable for the cradle of life at this time.
Fast forward to 3.8 billion years ago, in the Archean area, you will see bands of iron formations and deep layers of rock, dating the time of the oxygen revolution. Iron reacts highly with oxygen and will precipitate iron oxides. It is indicated that Earth was abundant in iron and reacted with the prokaryotic organisms that produce oxygen, which led to the Great Oxidation Event. This layer also contains stromatolites, which are sedimentary rock deposits in the ocean, containing microscopic life forms that have bacterial characters and can be found in shallow waters between Australia and Asia. These rock formations are made up of layers of colonized photosynthetic cyanobacteria. Later on, these prokaryotic species will become very important in one of Earth's evolutionary change to the biosphere. And what had occurred were these events that had unfolded. Geologists believed there was a heavy bombardment of asteroids and meteorites that struck Earth, causing an increase of volcanic activity, and craters were formed in the Earth's crust. Cosmic ice debris that come in contact with the Earth were thought to contain volatile molecules such as nitrogen, methane, water, carbon dioxide, and ammonia that were released on impact. Due to the intense heat of impact into Earth's orbit, these compounds vaporized into the atmosphere, creating a formation of clouds, causing lightning storms and rain. This rain cooled down the Earth for centuries and centuries. A study conducted in Russia discovered traces of isotopic tungsten in a layer of rocks that survived the first half of Earth history. Samples of meteorite debris they collected also contained traces of tungsten as well. Coincidentally, these traces can only be found in this layer of rock and meteorite samples. This evidence may support that theory of Earth event of asteroids collision and possibly how our oceans come from extraterrestrial origins.
In order for the sustainability of life, organisms must have a suitable environment to sustain growth, a source of energy, and be able to recycle within their source. And so far, after centuries of cooling, the oceans had become a suitable habitat for life to exist. But how did life actually begin? Well, Earth's early atmosphere, as we mentioned before, contained these gases: nitrogen, water vapor, ammonia, helium, hydrogen, and carbon dioxide, and yet no oxygen. Two scientists, Stanley L. Miller and Harold C. Urey, at the University of Chicago, used a closed compartment system to mimic Earth's oceanic and atmospheric prehistoric conditions. When they heated, electrified, and cooled each compartment, they sampled the content of water. At the end of their experiment, they discovered an extraordinary finding. According to an article from the University of Duke, Miller and Urey found that 10 to 15% of the carbon was in the form of organic compounds. 2% of that carbon have formed in the shape of proteins, which were used to make amino acids, which happen to be one of the essentials to cellular life. So what does this all mean? Life present at the time must have used and recycled volatile gases and other sources of elements before the appearance of oxygen. Could it be that the origins of prokaryotes were accumulations of protein and amino acids? Maybe. Evidence through geological records do show that bacteria have in fact existed before the time of the Great Oxidation event. Bacteria that we know that live in an environment free of oxygen are called anaerobic bacteria, meaning bacteria that reproduce in growing conditions that lack oxygen. There are many theories, including the Miller experiment, that hypothesize the origins of bacteria, but for now, we are going to focus on the very first bacteria that harnessed light as a source for energy.
Species of phototrophic bacteria that converted light energy to chemical energy and existed in the Archean era are separated into two categories of photosynthesis: anoxygenic and oxygenic. I will explain these terms in a moment. Scientists believe that anoxygenic bacteria came before oxygenic bacteria due to their photosynthetic primitive features. Here are a few reasons why. First, anoxygenic bacteria do not produce oxygen, hence the an in anoxygenic, an being the Latin root for against, while oxygenic bacteria produce oxygen at the end of their photosynthetic process. It would be ideal that organisms had a tactic to survive in anaerobic conditions. Second, anoxygenic photosynthesis is considered primitive to oxygenic photosynthesis because anoxygenic bacteria use other compounds such as hydrogen sulfide, iron, or nitrogen rather than water as a source of electrons to use in their electron transport chain that will, in fact, produce ATP, which happens to be located in photosystems 1. For example, purple sulfur bacteria live deep within the ocean, where they're exposed to low light conditions. They colonize on mounds of hydrothermal vents deep within the seabed that excrete black smoke rich in hydrogen sulfide. They reduce hydrogen sulfide to make sulfuric acid by fixing carbon dioxide and using hydrogen sulfide as a substrate for electrons to bounce on antenna complexes in their photosystem 1 and travel through their electron transport chain. Need a quick review? Cyanobacteria, a perfect example for oxygenic bacteria like modern algae and plants, have photosystems 1 and 2. So let's call them PS1 and PS2. Remember that in the process of photosynthesis, photons from the sun rays bounce on antenna pigments of PS2 and excite an electron held by a chlorophyll pigment. As you can see, during this cycle of reduction, the electron then travels into the electron transport chain and then into PS1. Just in case if you forgot, the reason why PS2 and PS1 are ordered in this way is because PS1 was discovered first and PS2 was discovered after. So, yeah. As you can see down here, something needs to replace that electron that bounces away. Well, PS2 is designed to split water and reduce oxygen to replenish that lost electron, and the cycle goes over again. Purple sulfur bacteria lack a photosystem 2, and the electrons are reduced in the photosystem 1. This evidence is crucial because it indicates that photosystem 2 is an evolutionary step for photosynthesis. Scientists, however, are unclear as to how cyanobacteria retrieved photosystem 1 and 2, but it is evident that oxygenic bacteria may be descendants from anoxygenic bacteria. Cyanobacteria may have been the culprit for a mass extinction to anaerobic bacteria, and oxygenic bacteria are intolerant of oxygen, and you can see how far apart purple bacteria are from the cyanobacteria in this chart. Cyanobacteria must have been very successful with this evolutionary advantage due to the fact that oxygen in fossilized evidence began to increase as layers ascend.
After 2 billion years of prokaryotic life, the oxygen concentration in the atmosphere reached about 2% of its present concentration in our atmosphere today. This wasn't very much oxygen, but its appearance coincides with the emergence of the eukaryotes. This was a gigantic step forward in the development of life on Earth. Not all eukaryotes use oxygen, but being able to use oxygen increased the diversity possible for eukaryotes. The earliest eukaryotes appeared 2 billion years ago.
Their evolution intriguingly corresponds with the rising oxygen levels. This is probably due to the evolution of the nucleus's need to protect the fragile DNA from oxidation. Endosymbiosis, in which mitochondria and chloroplasts were taken in as organelles, may have improved energy efficiency and recycling between previously free-living organisms. Chloroplasts are descended from cyanobacteria, the only prokaryotic group capable of oxygenic photosynthesis. As well as their sophisticated interior organization, improved DNA capacity, and genetic control, eukaryotes have one enormous advantage over prokaryotes, an evolutionary leap they made about 1 billion years ago.